Welcome to the sleeping mind and body. This is a calm space where we explore the human body and mind through slow, gentle explanations. You don't need to stay awake, focus, or remember anything. Simply listen and allow your thoughts to soften as your body rests. Tonight, we'll gently explore how the brain changes as we learn new things. If you fall asleep before the end, the video has done its job. Neuroplasticity is a simple word for a quiet, ongoing feature of the brain. It describes the brain's capacity to change with experience. Not as a sudden event, and not as a dramatic switch, but as a steady biological process that continues, in small ways, across time. The brain is alive, active, and responsive. As days pass, as sensations arrive, as thoughts repeat, the brain subtly adjusts itself. When people hear the word change, it can sound like something large and immediate. In the brain, change is often gentle. It happens through tiny shifts that add up slowly. Neuroplasticity is not a single mechanism. It is a broad idea that includes many kinds of adjustment. Changes in the strength of connections between cells, changes in how easily certain patterns of activity occur, and changes in the way networks cooperate. Much of it is so gradual that it is felt only indirectly, if it is felt at all. The brain is made of billions of nerve cells, called neurons, along with many supporting cells that help neurons function. Neurons communicate by sending signals to one another. They do not usually touch directly. Instead, they meet at small gaps called synapses. A synapse is a point of contact where one neuron can influence the next, using chemical messengers and electrical changes. In everyday life, this communication is constant. It supports seeing and hearing, moving and resting, remembering and forgetting, and all the quiet internal work of keeping a body coordinated. Neuroplasticity often refers to the way synapses change with use. When a pattern of activity happens again and again, the connections involved can become more effective. Signals may pass more easily, or more reliably, or with less effort from the surrounding network. When a pattern is less used, the opposite can happen. Connections can weaken. Some pathways may become less available, like a trail that grows faint when it is not walked. This is not a judgment of good or bad. It is a form of adaptation, an economical way for living tissue to respond to what tends to occur. In this way, learning is not only an idea in the mind, it has a physical side. Learning can be described as changes in the brain that make certain activity patterns more likely to happen again. A new skill, a new memory, a new familiarity with a place or a language, all correspond to shifts in how neurons and synapses work together. These shifts do not require drama. They are more like slow tuning than sudden rebuilding. It can be calming to imagine these changes as small adjustments, made quietly. A neuron does not decide to change, and the brain is not making plans in the way a person makes plans. Instead, cells follow biological rules. Activity leaves traces. Repetition matters because repeated activity gives the brain a consistent signal about what is worth maintaining. Over time, some synapses become stronger and some become weaker, and networks settle into patterns that match lived experience. Even the word stronger can be understood in a gentle way. A stronger synapse is often one that releases chemical messengers a little more readily, or that responds a little more efficiently, or that has slightly altered receptor numbers. These are small molecular events, repeated and stabilized. The brain does not have to change all at once. It can change in tiny steps, each step almost unnoticeable, until the overall pattern feels familiar. Neuroplasticity also includes the idea that the brain remains adaptable across the lifespan. The pace and style of plasticity can vary at different ages. In early life, change can be especially rapid, because developing brains are forming and refining large numbers of connections. Later on, change tends to be more selective and more dependent on context. But the capacity to adjust does not disappear. Adult brains still modify synapses, still reorganize networks, still respond to practice, novelty, and repetition. The changes may be slower, and they may require more consistent conditions, yet the underlying ability remains. It can help to think of the brain as a landscape of pathways. Some pathways are well established, supporting familiar actions and thoughts. Others are lighter, like soft impressions in the ground. When a certain pattern is used, it becomes easier to use again. When it is not used, it may fade. This image is not exact biology, but it matches the general direction of plasticity. The brain tends to reinforce what repeats and reduce what does not. At the same time, the brain also seeks balance. Change is not constant reshaping without stability. Plasticity works alongside processes that keep activity within workable ranges. Neurons must remain stable enough to function, even as they remain flexible enough to adapt. The brain is always negotiating between holding steady and adjusting, between preserving reliable patterns and allowing new ones to form. Rest is part of this negotiation. Much of the brain's change does not happen only in the moments of active effort. Some adjustments unfold during quieter periods, when the brain is not taking in new tasks. During sleep, for example, patterns of activity may be replayed in a softer form, and certain connections may be refined. Sleep can be seen as one of the brain's natural environments for reorganizing, sorting, and stabilizing. Not as a dramatic workshop, but as a calm biological setting where subtle changes can consolidate. This is why neuroplasticity can be described in a circular way, returning to the same idea from different angles. The brain changes with experience. Experience includes attention and repetition, but it also includes pauses, gaps, and rest. The brain strengthens some connections and loosens others. It forms patterns, then adjusts them, then stabilizes them again. The overall process is continuous, like slow weathering shaping a landscape. As you listen, you may notice that certain phrases return with slight differences. This is intentional, because neuroplasticity itself is not a straight line. It is not a single story with a clear beginning and end. It is a background process, always present, sometimes more active in one network and quieter in another. The brain is constantly responding to what happens, even in small and ordinary moments. So, neuroplasticity can be held in mind as a calm fact of living tissue. Neurons communicate across synapses. Patterns repeat. Some connections become easier to activate, and some become less likely. Over time, this is learning in its physical form. It is slow, gradual, and balanced by stability. It continues through life, adapting gently to what is repeated, what is practiced, what is sensed, and what is allowed to rest. And when the same ideas return again, in slightly new wording, it can mirror the brain's own way of working. Repetition with variation. Familiar patterns revisited. Small changes accumulating quietly. A steady system adapting, moment by moment, without urgency, and without needing to arrive anywhere in particular. Inside the brain, learning begins with living cells. These cells are called neurons. A neuron is a biological cell with a membrane, internal chemistry, and a need for balance. It takes in signals, it responds, and it returns to a steady state. When we speak about brain plasticity, we are often describing how neurons, together, shift the way they communicate over time. A neuron communicates in two main ways. Within the neuron, signals travel as electrical changes along its membrane. Between neurons, signals are passed across small gaps using chemicals. The electrical part is sometimes described as a brief wave of activity, a change in voltage that moves along the cell. The chemical part involves tiny packets of messenger molecules released from one neuron and detected by another. This combination of electrical and chemical signaling allows neurons to link their activity, not as isolated units, but as parts of a larger system. Neurons have branching shapes that help them connect. One side of the neuron receives input, often through many small branches. Another part of the neuron sends output, often through a longer fiber that reaches toward other cells. Where one neuron meets another, the connection is called a synapse. Synapses are not hardwired bolts or plugs. They are living contact points, maintained by proteins, membranes, and constant cellular work. They can become stronger, weaker, more efficient, or less responsive. In this quiet flexibility, brain change becomes possible. Learning is sometimes imagined as a single place where knowledge is stored, or a single kind of neuron that holds a memory. In reality, learning is better described as patterns of activity spread across many neurons at once. A single neuron may participate in many different patterns at different times. It may be active during one task, and then later contribute to a different task, depending on which other neurons are active with it. Learning is not usually housed in one learning cell. It is distributed, shared, and overlapping. When you recognize a familiar sound, when you remember a face, when you understand a word, it is not one cell performing the recognition. It is a coordinated pattern. Many neurons are active together, and their combined activity carries the meaning. The brain works through populations. Each neuron contributes a small part, and the whole pattern becomes the experience. These patterns can be thought of as networks. A network is simply a group of neurons that tend to influence one another through their connections. Some networks are local, involving nearby neurons. Some networks are wide, linking distant regions through long fibers. Networks are constantly active at low levels, shifting as attention, sensation, and internal states change. And as learning happens, networks can become more likely to form certain patterns again. One calm way to describe learning is to say that certain pathways become easier to travel. A pathway is not a single wire. It is a route through a network, from one group of neurons to another, through many synapses. When a pathway is used repeatedly, the synapses along that route can adjust. Chemical release may become more reliable. Receptors may become more responsive. The timing between neurons may become more coordinated. Over time, the pathway may become more likely to activate when a similar situation occurs. This is a gentle shift in probability. The brain does not need to rebuild itself overnight. Instead, small adjustments accumulate. When two neurons tend to be active around the same time, their connection may become more effective. When activity does not occur together, connections may remain the same or gradually become less influential. In this way, the brain's network reflects its history of patterns, signals, and repeated coordination. Cells, signals, patterns. These three ideas can return again and again. Neurons are cells. They send and receive signals. And learning is the stabilization of certain patterns across many cells. The pattern is not fixed like a photograph. It is more like a familiar rhythm that can be played again. When the conditions are similar, the network falls into a similar pattern, because the connections make that pattern slightly easier to reach. Even at rest, neurons are not completely silent. They maintain gradients of ions across their membranes, keeping a readiness to respond. They regulate internal chemistry, repair components, and recycle materials. This background work supports signaling later on. When a neuron sends an electrical signal, it is using energy, and afterward it must reset. It must restore balance. Learning depends not only on activity, but also on recovery, because living cells need time to return to equilibrium. Synapses also require maintenance. They are shaped by the traffic that passes through them, but they are also shaped by the cell's housekeeping. Proteins are made and broken down. Receptors are moved in and out of the synaptic membrane. The structure of the synapse can subtly change, becoming more stable or more flexible. These changes are part of plasticity. They are not dramatic. They are gradual, molecular, and quiet. When we say that neurons fire together, we are describing coordination in time. Timing matters because neurons are sensitive to when signals arrive. If inputs come in close sequence, the neuron may respond more strongly. If signals are scattered, the response may be different. Over repeated experiences, timing relationships can become more consistent within a network. A learned pattern often includes a learned timing, not just a set of active cells, but a coordinated sequence across them. In a changing network, the same neurons can participate in many different pathways. This is one reason learning can be flexible. A neuron is not dedicated to one memory for life. It is a living cell, adjusting its connections within constraints. It can be part of an old pattern and still be recruited into a new one. The brain balances stability and change, keeping useful pathways available while allowing new pathways to form. Across the lifespan, neurons and networks continue to adapt. In early life, many connections are formed and reshaped quickly. Later, change can still occur, often in more subtle ways, through refinements of existing networks and selective strengthening of certain pathways. The details vary across brain regions, but the general principle remains calm and consistent. Cells communicate with signals, and repeated patterns shape the network. It can be soothing to picture learning as a quiet conversation among cells. Electrical signals move along membranes, chemical signals cross synapses, and networks settle into familiar patterns. With repetition, some pathways become more likely to activate. With rest, cells restore their balance and support the long-term stability of synapses. And over time, in small steps, the living network continues to change. Cells, signals, patterns. Neurons as living cells in a changing network. Not a single learning cell, but many neurons working together, forming activity across pathways that become gently easier to use again. A brain is never perfectly still, and it never needs to rush. It adjusts in small increments, guided by the simple biology of communication, coordination, and quiet renewal. Inside the brain, neurons do not usually touch one another directly. Instead, they meet at small junctions called synapses. A synapse is a carefully arranged gap where one neuron can influence the next. The first neuron sends a signal down its length, and at the synapse it releases tiny packets of chemical messenger. Those molecules drift across the narrow space and bind to receptors on the neighboring neuron. In this quiet exchange, one cell's activity becomes a gentle nudge on another cell's state. Synapses are not all identical. Some are built for fast, strong influence, and some for slower, softer influence. Some sit on the branches of a neuron, on thin spines that can subtly change shape. Others connect closer to the cell body, where their effect can be more direct. Yet across these different forms, the basic idea stays the same. A synapse is a point of contact where information can be passed along, where a pattern can continue, and where a pathway can become more or less likely to be used again. When people speak about learning in the brain, much of what they mean can be described through changes at synapses. Learning is not usually a single switch turning on. It is more often a gradual adjustment of how strongly one neuron affects another. If a particular pathway is used repeatedly, the synapses along that route can become slightly more effective. If a pathway is rarely used, the synapses may become slightly less effective. This is not a dramatic transformation in a moment. It is a slow shift, in small increments, repeated many times. Synaptic strength is a simple phrase for a complex set of processes. It refers to how likely a signal from one neuron is to influence the next neuron, and by how much a stronger synapse might release more chemical messenger, or the receiving side might respond more readily, with more receptors available or with receptors that open more easily. A weaker synapse might do the opposite, releasing less messenger, or producing a smaller response. Often the differences are modest. A synapse does not have to double its effect to matter. In a network made of billions of neurons and countless connections, small changes can add up quietly. One way to describe these changes is through two complementary ideas: long-term potentiation and long-term depression. These terms sound heavy, but the meaning is straightforward. Long-term potentiation, often shortened to LTP, is a lasting increase in synaptic strength. It is the synapse becoming a bit more effective at passing a signal. Long-term depression, often shortened to limited, is a lasting decrease in synaptic strength. It is the synapse becoming a bit less effective. In both cases, long-term does not mean permanent or unchanging. It simply means that the change lasts beyond the immediate moment, continuing after the original activity has passed. LTP is sometimes introduced with the idea that neurons that fire together, wire together. That phrase is only a rough summary, but it points to an important pattern. When the sending neuron and the receiving neuron are active in a coordinated way, the synapse between them may be adjusted upward. The brain treats this coordination as meaningful. It is as if the circuit is quietly noting, again and again, that these signals tend to belong together. Over time, the synapse becomes a slightly more reliable bridge. Limited can be understood in a similar, calm way. When activity is uncoordinated, or when a pathway is used less often, the brain may reduce the strength of certain synapses. This is not damage, and it is not failure. It is a kind of tuning. Weakening some connections can prevent the network from becoming too noisy, too crowded with competing signals. It can help preserve balance, allowing important patterns to stand out more clearly against background activity. In this way, strengthening and weakening work together, like slow adjustments of volume knobs across a large soundboard. At the microscopic level, these adjustments involve many small mechanisms. A synapse can change the amount of chemical messenger released. It can change how quickly the messenger is cleared away. It can change the sensitivity of the receptors on the receiving side. It can alter the shape of the tiny spine that holds the synapse, making room for more receptors or fewer receptors. Some changes are quick and reversible, like shifting resources toward an active connection for a while. Other changes are stabilized by longer processes inside the cell, including changes in which proteins are built and how they are arranged. Even when we speak calmly about strengthening and weakening, it may help to remember that no single synapse carries a whole memory or a whole skill by itself. The brain does not store learning in one isolated place. Change is distributed. Many tiny adjustments occur across many synapses, spread over multiple areas and layers of processing. A skill as simple as recognizing a familiar sound can involve coordinated activity across sensory regions, association regions, and systems that influence attention and prediction. Each region contributes its own subtle shifts, each with countless synapses changing by small amounts. This distribution matters because it makes learning resilient. If one connection is altered slightly, the network still functions. If a few synapses drift in strength, the overall pattern can remain stable because it is supported by many pathways. Learning is often less like carving a single deep groove and more like gently reshaping a landscape, grain by grain. Over time, routes become easier to travel, not because one bridge is built, but because many small crossings become a little more passable. Repetition is one of the simplest ways these changes accumulate. When a pattern repeats, synapses involved in that pattern are activated again and again. Each activation is an opportunity for a tiny adjustment. The changes can be so small that they are invisible from moment to moment, yet they can become meaningful across hours, days, or longer. This is why learning often feels gradual. The brain is not usually announcing its edits. It is making them quietly, behind the scenes, through steady biochemical steps. At the same time, the brain avoids changing everything all at once. If every active synapse strengthened endlessly, the system would lose balance. So plasticity is guided by stabilizing forces. Some synapses strengthen while others weaken. Some changes are allowed only when certain conditions are met, such as particular patterns of timing, or the presence of chemical signals that indicate importance or novelty. In this way, plasticity remains controlled. It is flexible, but not chaotic. It can be soothing to imagine synapses as adjustable junctions, each one capable of a small shift, up or down, as experience flows through the nervous system. A thought, a sound, a movement, a word, a familiar face, each can send ripples through networks. The ripples do not usually leave a single mark. They leave many small traces, scattered across synapses, like faint changes in pressure on many tiny springs. Long-term potentiation and long-term depression are names for these faint but lasting changes. They are part of how the brain records patterns without needing a central editor. The adjustments are local. Each synapse responds to the activity passing through it, shaped by timing and by the chemical environment around it. And yet, taken together, these local changes can support large-scale shifts in what the brain can recognize, predict, and produce. So when learning happens, it can be pictured as a distributed, quiet recalibration. Many synapses adjusting by a small amount, many times over. Some becoming a bit more responsive, some becoming a bit less. A wide network, slowly changing its tendencies. Not with a sudden transformation, but with a calm accumulation of tiny differences, spread out across the brain's innumerable junctions, repeating and settling, as signals continue to pass from neuron to neuron. When something is repeated, the brain often responds with repeated activity. A similar set of neurons becomes active again, and many of the same connections are used again. In quiet scientific terms, repetition can be described as the repeated activation of neural pathways. Each time a pattern of activity returns, signals travel along familiar routes, passing from one neuron to the next at synapses, where chemical messengers and electrical changes help information move forward. A neural pathway is not a rigid wire. It is more like a preferred route that can become easier to travel over time. When activity follows a similar path again and again, the brain may adjust in small ways so that signaling along that path becomes more efficient and more reliable. This does not necessarily mean that everything becomes stronger in a simple sense. Some connections may be reinforced, while others are quieted or refined, allowing the overall pattern to become clearer, more consistent, and less noisy. At the level of single synapses, a repeated pattern of use can slightly change how easily one neuron influences another. If a presynaptic neuron tends to become active shortly before a postsynaptic neuron, the timing between them can matter. The brain is sensitive to coordination. When activity is coordinated in a consistent way, synapses can be adjusted so that the next time the same pattern returns, it is more likely to unfold smoothly. This kind of timing-based shaping is one reason repetition has such a strong relationship with plasticity. It is not only the number of times something happens, but also the relative timing, the rhythm, and the coherence of the activity across a network. Efficiency in the brain often means that less effort is needed to produce the same pattern. A signal may propagate with fewer delays. Neurons may fire with slightly better precision. Supporting cells may contribute to keeping the environment stable, helping ions and neurotransmitters return to balanced levels after activity. With repeated activation, the brain can become better at setting up the conditions that let the same pathway activate again without difficulty. Reliability can increase, not as a dramatic change, but as a gradual tendency for a familiar pattern to repeat in a familiar way. It can be calming to picture repetition as a gentle returning. The network activates, then settles. Later, it reactivates, then settles again. In these cycles, small adjustments accumulate. Some synapses may release neurotransmitter a bit more readily. Some receptors on the receiving side may become slightly more responsive. The shape of tiny structures on neurons, such as dendritic spines, can subtly shift over time, reflecting the history of use. These changes are not always permanent. Some are short-lived, lasting minutes or hours, while others can be stabilized if similar patterns continue to recur. Repetition also interacts with what the brain does between moments of activity. After a burst of signaling, neurons and synapses need time to restore their readiness. Neurotransmitters are recycled or broken down. Ion gradients are re-established. Metabolic resources are replenished. The brain is not only active, it is also constantly resetting. In that resetting, the conditions for future activity are prepared. So the effects of repetition are often shaped by alternating phases: activation and recovery, firing and quiet, engagement and rest. When a pattern is re-encountered, the brain does not start from zero. It begins from whatever state was left by prior encounters. If a pathway has been used recently, it may be temporarily more likely to activate again, a phenomenon sometimes described as priming. If a pathway has been used many times over longer spans, structural and molecular changes can make it more stable. In both cases, what matters is that the brain carries a history, and repetition is one way that history becomes written into the probabilities of future activity. Timing and coordination are especially important because the brain is made of many parts acting together. Learning-related activity rarely involves a single synapse in isolation. Instead, groups of neurons fire in patterns, and those patterns interact. When different inputs arrive in a coordinated way, they can amplify one another, making it more likely that a downstream neuron will fire. When inputs arrive out of sync, they may not combine as effectively. Over time, this can shape synapses so that coordinated pathways become more influential, while uncoordinated ones contribute less. In this way, repetition is not only about doing the same thing again. It is about the brain recognizing a recurring relationship in time. One gentle way to think about this is to imagine the brain listening for regularities. When a pattern returns with similar timing, similar order, and similar context, the brain can treat it as a reliable event in the environment or within the body. Synapses can adjust so that the network responds to that event with slightly improved predictability. The brain becomes, in a quiet sense, more prepared for the same pattern to occur again. The phrase, "cells that fire together wire together," is often repeated, though it is a simplification. What it points to is the idea that near simultaneous or consistently ordered activity can strengthen particular connections. But the full picture includes balance. Some forms of plasticity strengthen synapses, while others weaken them, preventing runaway excitation and keeping networks stable. Repetition can therefore lead to refinement as much as reinforcement, shaping a pathway so it is not only stronger, but also more selective, more controlled, and better integrated with other pathways. As similar activity is repeated, the brain may also adjust the insulating layers around some axons, called myelin. Myelin can influence how quickly signals travel. Changes in myelination tend to be slower than synaptic changes, developing across days, weeks, or longer. But they can contribute to the feeling of smoothness and reliability in well-used circuits, because the timing between distant regions can become better coordinated. Again, the key idea is not sudden transformation, but gradual tuning. Repetition can be understood as reactivation, as returning, as re-encountering. Each return is an event in time, and the brain is a system that responds to events by changing its likelihoods. It adjusts what it expects, how it routes signals, and how easily certain patterns come online. Those adjustments are subtle, distributed, and often reversible. They are also constrained by the need for stability, because a brain that changed too fast would not hold onto anything long enough to be useful. Even within a single day, the brain can carry traces of repeated patterns. Some traces are maintained by ongoing chemical signaling inside neurons, keeping certain synapses more ready than others. Some traces fade if they are not revisited. Others become more durable when they are revisited, not through force, but through recurrence. This is one of the quiet themes of plasticity. Patterns that return can leave a deeper imprint than patterns that appear once and never return. And still, repetition does not act alone. The brain is always balancing change with conservation. It is always integrating new activity into existing networks, and existing networks into new situations. Repeated patterns of activity are one way the brain gently reshapes itself, increasing efficiency, improving reliability, and refining timing. In the background of awareness, neurons fire and rest. synapses adjust and settle, and the same pathways can be activated again and again in a slow, natural rhythm. Inside the brain, much of learning is carried by very small events, repeated quietly. Neurons communicate, not only through electrical changes that move along their branches, but also through chemical messages that cross tiny gaps. These gaps are called synapses. At a synapse, one neuron releases molecules into a narrow space, and the next neuron detects them. This is one of the main ways signals travel from cell to cell, and it is also one of the main places where the brain can change with experience. The chemical messengers released at synapses are called neurotransmitters. They are stored in small packets inside the sending neuron, and when the right electrical pattern arrives, some of these packets merge with the cell's membrane and release their contents. The neurotransmitter molecules drift across the synaptic space, bind to receptors on the receiving side, and influence what happens next. The whole process is brief, and then the molecules are cleared away, either taken back up into cells or broken down. This helps each message stay distinct, and it keeps the system steady over time. Different neurotransmitters can have different effects, depending on which receptors are present and what the receiving neuron is doing at that moment. Some receptors tend to make the next neuron more likely to fire, and some tend to make it less likely. In many circuits, learning involves a careful balance between excitation and inhibition, between signals that nudge activity upward and signals that quiet it down. The brain does not simply amplify everything. It adjusts. It steadies. It maintains a workable range, even while it remains flexible. When people learn, synapses can change in ways that alter how neurotransmitters are released, how strongly receptors respond, or how quickly signals are cleared. Over repeated activity, a synapse may become more reliable, releasing transmitter with a slightly higher probability, or it may become more sensitive on the receiving side, adding more receptors or changing how those receptors behave. In other cases, synapses can weaken, becoming less likely to pass on a signal. These changes can be small in any single moment, yet meaningful when they accumulate across many synapses and many repetitions. Alongside neurotransmitters, the brain also uses chemical signals known as neuromodulators. Neuromodulators do not always carry a precise, point-to-point message in the same way. Instead, they often adjust the general state of a network, shifting how responsive neurons are, how strongly synapses change, and how attention and learning conditions are shaped. They can be thought of as setting a background tone, not as an emotion or a command, but as a context in which ordinary synaptic messages are interpreted. Dopamine is one example of a neuromodulator that influences learning and adaptation. In many parts of the brain, dopamine signals are related to how outcomes compare with expectations, and this can affect which connections are strengthened or weakened over time. Dopamine does not act alone, and it does not create learning by itself. It changes the likelihood that certain patterns of activity will leave a lasting trace in synapses. It is part of the brain's way of marking some moments as more informative than others, in a calm, chemical way, through concentrations and timing. Acetylcholine is another neuromodulator, often linked with attention, arousal, and the selection of information. In sensory regions, acetylcholine can sharpen responses to certain inputs and reduce the influence of background noise. In learning, this can make the brain more ready to adjust its connections based on what is being processed. Again, this is not a dramatic switch. It is a gradual adjustment in how open a circuit is to change, and how clearly signals stand out. Norepinephrine, sometimes called noradrenaline, is also part of this landscape. It is often associated with alertness and responsiveness to novelty, and it can shift the brain toward a state where incoming signals are handled a little differently. It can alter the gain of neural responses, making some signals more prominent and shaping how synapses respond to repeated activity. Like other neuromodulators, norepinephrine works through slow, widespread influences as well as more local effects, helping tune the brain's readiness to update. These neuromodulators are released by specialized groups of neurons, often located in deeper brain regions, with long-reaching connections. Their signals can spread across broad areas, bathing many synapses at once in a slightly altered chemical environment. That environment can change from moment to moment, and also across longer timescales, depending on the rhythms of waking and resting, and on the brain's ongoing needs. Learning is not only about the messages that travel across individual synapses. It is also about the conditions under which those messages arrive. The brain's local environment is shaped not only by neurons, but also by glial cells. For a long time, glia were described mainly as support cells, and support is still a good word, but it is a living kind of support, active and responsive. Glial cells help regulate the space around synapses. They manage chemicals, maintain the right balance of ions, and help keep communication stable. They influence how quickly neurotransmitters are cleared, and they can affect how efficiently signals are passed along. One important type of glial cell is the astrocyte. Astrocytes extend fine processes that come close to many synapses. They can take up neurotransmitters after release, helping end the signal at the right time and preventing spillover. They also help regulate levels of important molecules in the extracellular fluid, keeping conditions within a range that neurons can use. This is part of what makes the brain signaling precise. Messages are allowed to happen, and then they are gently contained. Another type of glial cell, the oligodendrocyte, is involved in myelin, the insulating layer around many axons. While myelin is not itself a chemical messenger across synapses, it influences the timing and efficiency of electrical signals arriving at synapses. Small changes in myelination can affect how patterns of activity line up in time, and timing matters in learning. The brain pays attention to when signals arrive, not only to whether they arrive. In that sense, the local environment includes both chemistry and conduction, both the synapse and the path leading to it. Microglia, another class of glial cells, are involved in monitoring the brain's tissue environment. They respond to changes and help maintain healthy function in development and also across life. Microglia can be involved in synaptic remodeling, participating in the gradual reshaping of connections. This is not a loud or abrupt process in everyday terms. It is part of the brain's constant maintenance, a quiet background activity that helps networks remain adaptable without becoming unstable. All of these elements, neurotransmitters, neuromodulators, and glial support, contribute to a sense of balance. Signals are sent, received, and cleared. Sensitivity rises and falls. Circuits become slightly more ready to change, then slightly less. The brain stays within workable limits while still allowing learning to proceed. In a stable chemical environment, small differences can matter. A modest shift in receptor activity, a slight change in transmitter availability, a subtle adjustment in neuromodulatory tone can shape which connections strengthen with repetition and which fade with disuse. Over time, learning can be seen as a pattern of chemical events, repeated and regulated. A neurotransmitter crossing a synapse, a receptor opening, an ion flowing, a molecule being recycled. a neuromodulator spreading through a region, altering responsiveness in a gentle gradient. A glial cell clearing the space, maintaining concentrations, and supporting steady communication. It is a world of small movements and careful timing, where change happens through many quiet steps. Even rest fits naturally into this picture. When activity patterns shift during restful states, the chemical environment also shifts. Levels of certain neuromodulators change with sleep and waking rhythms, and synapses may become more or less prone to adjustment. The brain continues to regulate itself, not as a separate task, but as part of its normal life. Learning, in this view, is not a single event. It is an ongoing balance between signaling and stability, between change and preservation, carried forward by chemical messengers moving through a carefully maintained environment. And as this chemical conversation continues, moment after moment, the brain remains softly dynamic. Messages cross synapses. Background tones rise and fall. Support systems keep the space clean and the timing steady. In that calm interplay, the capacity to adapt remains present, not as a sudden transformation, but as a gradual, regulated process, unfolding quietly within the brain's local environment. When the brain begins to learn something, many of the earliest changes are small, quick, and reversible. They are not yet the kind of lasting change that becomes part of a long-term skill or memory. Instead, they are short-term shifts in how easily neurons communicate, and how ready a circuit is to respond. For a little while, a pathway can become more responsive, as if the volume on a connection has been turned slightly up, or slightly down. These changes can last seconds, minutes, or sometimes longer, and then gently return toward an earlier state. One way to imagine short-term plasticity is as a temporary adjustment to ongoing activity. When neurons fire close together, chemical messengers move across synapses, and the receiving cell responds. If this happens repeatedly over a short time, the synapse may briefly change how much neurotransmitter it releases, or how sensitive the receiving side becomes. Some synapses become momentarily facilitated, passing signals along with a little more ease. Others become momentarily depressed, as if resources have been used up and need time to recover. In either case, the brain is not committing yet. It is sampling, adjusting, and keeping the system flexible. Short-term plasticity is often about immediate context. It helps the brain handle streams of information that arrive in clusters, like sounds in speech, or a sequence of movements, or a set of visual details. It can support attention and working memory, not by storing a permanent record, but by keeping certain patterns more available for a brief period. The brain can hold a kind of readiness, where a circuit is primed to activate again. And then, if the pattern is not repeated, that readiness fades, quietly and without effort. This gentle fading is not a failure. It is part of the design. If every small experience became permanent, the brain would become crowded with noise. Instead, the nervous system keeps options open. It allows many temporary changes to occur, then lets most of them dissolve. A small fraction, under the right conditions, move gradually into longer-term stabilization. That slower shift is often described as consolidation. Consolidation is not a single moment when a memory is saved, like a file being written once to a disk. It is more like a gradual settling. A pattern of activity that appears again and again can become easier to recreate. The brain does not store the event as a perfect copy. Instead, it strengthens certain relationships between neurons, making some pathways more likely to activate together in the future. In consolidation, The timing of signals matters. When groups of neurons repeatedly fire in related patterns, the synapses between them can change in ways that outlast the immediate moment. Over time, a circuit can become more stable, meaning it can produce a familiar pattern of activity with less effort and less variability. At the same time, other circuits remain flexible, ready to adjust when new information arrives. Some parts of consolidation involve chemistry that unfolds slowly. Inside neurons, molecular signals can lead to changes in gene expression and the creation of new proteins that support longer-lasting synaptic change. This is one reason consolidation takes time. It depends on processes that are measured in hours and days, not only in seconds. The brain is not rushing. It is balancing stability with the ability to change again. Rest fits naturally into this picture. When the brain is not actively taking in new input, it is still active, but in a different way. Patterns that occurred during wakefulness can be replayed in quieter forms, as if the nervous system is reviewing its own recent activity. This replay does not feel like deliberate practice. It is more like gentle internal repetition, happening in the background. Across periods of rest and sleep, some synapses keep the changes that matter, while others drift back toward baseline. In this gradual movement from short-term change to longer-term stabilization, structural plasticity becomes more visible. Structural plasticity refers to small physical changes at synapses. A synapse is not a fixed object. It can grow, shrink, multiply, or simplify. On the receiving side of a synapse, tiny protrusions called dendritic spines can change shape. They may become slightly larger or more stable when a connection is used often, and slightly smaller or more transient when it is not. Structural plasticity also includes changes in receptor placement. Receptors are proteins that sit in the membrane of the receiving neuron, ready to respond to neurotransmitters. The number of receptors at a synapse, and where they are positioned, can shift. When a synapse becomes stronger, it may recruit more receptors or anchor them more effectively, making the same chemical signal produce a larger electrical response. When a synapse becomes weaker, receptors may be removed or become less available, making the connection quieter. These changes are still modest at the scale of a single synapse. They are microscopic adjustments, repeated across many connections. But over time, the accumulated effect can be meaningful. A skill becomes smoother. A familiar route of thought becomes easier to follow. A sequence becomes more likely to emerge in the same order. Not because the brain has become rigid, but because it has increased the probability of certain patterns. At the same time, weakening is just as important as strengthening. The brain continually prunes and refines. Connections that are rarely used may lose strength, not abruptly, but gradually. Some synapses remain possible but less likely. Others may be removed as networks reorganize. This allows the brain to preserve capacity. It reduces interference, so that older patterns do not drown out newer ones, and so that learning remains possible. In this way, plasticity is always a negotiation between change and stability. Short-term plasticity allows quick adjustments, like shifting balance while walking across uneven ground. Consolidation allows certain adjustments to settle into more reliable forms, like a path becoming smoother after many footsteps. Structural plasticity provides a longer-lasting foundation, with changes in synapse size, number, and receptor arrangement. And throughout it all, the brain maintains a quiet preference for flexibility, strengthening some patterns while letting others fade. It can be calming to remember that much of this happens without conscious effort. Neurons respond to activity, synapses adjust, and networks gently reshape. Some traces become stable enough to return, even after long gaps. Other traces dissolve, leaving only a faint readiness that can be rebuilt if needed. The brain does not treat every moment as equally important. It tests patterns, keeps the ones that fit, and releases the rest. So learning can be seen as a slow, biological sorting process. Brief changes appear, linger, and either settle or soften. Over hours and nights, over repeated experiences and quiet intervals, certain connections become more efficient, more coordinated, more likely to activate together. And even then, nothing is permanently fixed. The brain continues to keep options open, holding a steady balance between what is stable and what is still free to change. Learning does not only happen in the bright, active moments when attention is turned outward. Some of the changes linked to learning continue when the outside world becomes quieter, when movement slows, and when new information is no longer arriving in a steady stream. In the brain, activity and rest are not opposites that cancel each other out. They are parts of the same cycle, with different kinds of work happening in each. When you are awake and engaged, networks of neurons respond to what you see, hear, and do. Signals travel along familiar pathways and sometimes along new ones. Synapses, the small connection points between neurons, can become slightly more effective when they are used, and less effective when they are not. This is often described as synaptic plasticity. It is not a single event, and it is not always dramatic. It is more like a gradual adjustment, a shifting of probabilities. Certain patterns become a little easier to activate, while others fade into the background. As external input reduces, the brain does not simply switch off. Even in quiet wakefulness, when the eyes are closed or the mind is not focused on a task, the brain continues to generate internal activity. Some regions show rhythms that become more regular. Networks that were active during the day can still be active in softer ways, as if the brain is moving through stored patterns without needing new sensory material to drive them. Sleep is one of the clearest examples of learning's quieter side. During sleep, the brain remains active, but the activity is organized differently. The chemical environment changes. The balance between different rhythms shifts. Some signals that support alertness and immediate response become less dominant, and other processes that favor internal organization become more prominent. In broad terms, sleep can be described as a time when the brain replays and reorganizes patterns. This idea comes from observations that neural activity recorded during waking experiences can appear again later, during sleep, in a compressed or altered form. The replay is not like watching a perfect recording. It is more like revisiting fragments, strengthening certain relationships, and allowing the nervous system to test how pieces might fit together. Patterns related to movement, sound, space, and sequence can re-emerge, sometimes in the regions that first handled them, and sometimes in connected regions that help integrate them into wider networks. This reactivation can support consolidation, a word used to describe the stabilization of changes that were first set in motion during learning. During waking life, synapses may change quickly in response to use, but quick change can be fragile. Over time, some of these modifications become more durable, involving shifts in receptor activity, changes in gene expression, and adjustments in the structure of synapses themselves. Sleep is often associated with this slower phase, when the brain is less occupied with incoming demands and can devote more resources to internal maintenance and integration. Different stages of sleep appear to support different kinds of organization. Some stages are marked by slow, large brainwaves that travel across wide areas, as if coordinating broad regions into a shared rhythm. Other stages include faster activity and vivid internal experiences. Rather than treating sleep as one uniform state, it can be seen as a sequence of conditions, each offering a different style of processing. Across the night, these stages cycle, returning again and again, allowing learning-related changes to be revisited from multiple angles. A useful way to think about this is that waking life tends to emphasize encoding, the initial registration of experience, while rest and sleep can emphasize refinement. Refinement does not mean improvement in a motivational sense. It means the nervous system adjusts what it has taken in, shaping it so it can coexist with everything else already stored. New patterns have to find a place among older patterns. Some can be linked to what is already known, making retrieval easier. Others may be set aside or weakened if they are not consistent, not repeated, or not relevant to ongoing needs. This brings in the idea of balance. If every synapse only became stronger, without any counterweight, the brain would gradually become saturated. Activity would become less selective, more noisy, and less stable. The nervous system appears to have mechanisms that prevent this kind of runaway strengthening. One proposed mechanism is synaptic downscaling, a process in which synaptic strengths are adjusted downward across many connections, in a broad and gentle way. The word downscaling can sound harsh, but the idea is simple. The overall level of synaptic strength is nudged back toward a stable range, while the relative differences between connections can be preserved. In that sense, downscaling is not erasing learning. It can be viewed as restoring contrast. If all signals are amplified, none stand out. By reducing the general volume, the brain may keep the strongest and most consistent patterns distinguishable. Connections that were repeatedly used, or that fit well with existing networks, may remain relatively stronger than those that were only briefly activated. The system stays flexible, capable of future change, without becoming overwhelmed by the accumulation of small increases. Rest, then, can be understood as a time when the brain is both conserving and selecting. It is conserving energy by reducing the need for constant response to the environment, and it is selecting which changes to keep, which to soften, and how to distribute resources across networks. This selection does not require conscious effort. It can happen through the ordinary rules of neural activity. What reactivates tends to be maintained, what stays silent tends to weaken, and what is coordinated across regions tends to become more integrated. There is also a physical side to this quiet work. Synapses are biological structures, built and maintained by proteins, membranes, and support cells. During rest and sleep, the brain's housekeeping systems can shift into different modes, clearing byproducts of activity and restoring the conditions needed for stable signaling. This does not separate from learning. It supports it, because learning depends on a brain that can maintain its internal environment while still allowing change. Across the lifespan, these cycles of activity and offline processing continue. In childhood, when the brain is especially plastic, sleep is abundant, and many networks are being organized for the first time. In adulthood, plasticity remains, though it can become more selective and shaped by long-established patterns. In later life, the brain still adapts, still adjusts synapses, still uses periods of reduced input to reorganize and maintain balance. The details vary, but the overall rhythm remains recognizable. Experience during waking, quiet reactivation and recalibration during rest, and a gradual reshaping of networks over time. It can be calming to picture learning as something that does not demand constant effort, because the nervous system has built-in phases for working without conscious attention. The brain listens and responds when the world is active, and it also continues in a softer way when the world fades. In the quiet periods, connections are gently tuned, patterns are revisited, and the overall system is kept within stable limits. Activity gives the brain new material, and rest gives the brain a chance to arrange it, to reduce excess, and to keep what fits. And so the offline side of learning can be imagined as a slow nighttime tide. Experiences from the day leave subtle traces in networks of neurons. Later, during rest and sleep, those traces can be replayed in fragments, reorganized, and balanced against the whole. Some synapses are supported, others are reduced, and the brain continues, quietly, in its ongoing work of adapting. In early life, the brain is changing at a remarkable pace, quietly shaping itself around the steady stream of new sensations and new experiences. Neurons are growing, extending branches, and forming many possible connections. Synapses appear in large numbers, and circuits are tested and adjusted again and again. It is not a single moment of change, but a continuous process, as the nervous system learns what patterns are common, what signals matter, and what responses tend to work in the body's everyday environment. During infancy and childhood, plasticity is often described as heightened. That does not mean the brain is unfinished in a simple way. It means that many networks are especially ready to be shaped by experience, especially in areas related to perception, movement, and language. When a child hears speech, sees faces, reaches for objects, or learns to balance and walk, the brain is not only storing information. It is refining how signals are routed. It is strengthening some connections and allowing others to fade. Synapses that are used frequently tend to become more effective, and synapses that are rarely used may weaken over time. This gentle selection helps the brain become more efficient at handling the world it is actually living in. As development continues, plasticity does not vanish. It slowly changes its character. The brain begins to settle into more stable patterns, not because change is no longer possible, but because stability is useful. Stable circuits allow reliable perception, coordinated movement, and consistent understanding. At the same time, the brain remains capable of reorganization. It is still able to alter synaptic strength, still able to form new connections, and still able to reassign roles among networks when conditions shift. One way to think about this change across the lifespan is that early life often involves broad flexibility, while later life tends toward more selective flexibility. In childhood, many kinds of experience can leave strong marks on the structure and function of circuits. With age, plasticity becomes more dependent on specific experiences, repeated patterns, and meaningful contexts. Learning in an adult brain often relies on focused adjustments within established networks. Rather than building everything from the beginning, the adult brain modifies what is already there, fine-tuning circuits that have been shaped by years of sensory input, habits, and memory. Even so, adult plasticity is real and measurable. When people practice new skills, synapses can strengthen in relevant circuits. The timing of activity between neurons can change, making certain pathways more likely to activate together. New dendritic spines, small structures that help form synapses, can appear and stabilize with use. Some synapses may become less responsive if they are no longer part of a frequently used pattern. These are quiet, local shifts that accumulate. They can be subtle from one day to the next, yet clear across weeks, months, and years. Across all ages, the brain is balancing two needs that exist at the same time. One need is to remain adaptable, able to learn and adjust to new information. The other need is to remain stable, able to preserve memories, skills, and a coherent sense of how to navigate familiar environments. Plasticity is not simply more or less. It is shaped by this balance. The brain changes in ways that protect what is already working while still leaving room for updating and refinement. As the years pass, another process becomes increasingly important in the background: myelination. Myelin is a fatty insulating layer that wraps around parts of axons, the long fibers that carry electrical signals from one neuron to another. Myelin does not carry the signal itself. Instead, it helps the signal travel faster and more reliably, reducing loss and improving timing. In that sense, myelination supports efficiency. It helps neurons coordinate their activity with greater precision, which is useful for complex skills that depend on accurate timing, such as fluent movement, stable attention, and the rapid integration of information. Myelination develops over a long time scale. It begins early in life but continues through childhood and adolescence, and in some regions it continues into adulthood. This long progression matches the idea that the brain is not only building connections, but also refining how those connections operate. It is not just the presence of a pathway that matters, but how well it conducts signals, and how consistently it does so. Myelination can be seen as a kind of supportive remodeling, improving the performance of circuits that are repeatedly used. Plasticity and myelination can work together. When a network is active again and again, synapses may strengthen, and the axons involved may also become more efficiently insulated. Over time, the repeated use of certain pathways can contribute to smoother and faster communication within those circuits. This does not happen instantly. It is a gradual biological adjustment, one that reflects the brain's tendency to invest resources in what is reliably needed. In older age, the pattern continues. The brain is still plastic, but the pace of change may be different, and the conditions that support change can shift. Some kinds of learning may take longer. Some adjustments may require more repetition to become stable. At the same time, the brain carries a long history of structured networks, and that history can be helpful. Many skills become deeply practiced and well supported, and many forms of knowledge are organized into rich frameworks. Plasticity in later life often involves working within these established structures, adding new details, linking new information to older memories, and adjusting strategies rather than rebuilding from the beginning. It can be calming to remember that the brain's ability to change is not a temporary feature of youth. It is a basic property of nervous tissue. Neurons communicate, and communication alters neurons. Synapses respond to patterns of activity, and patterns of activity reflect lived experience. This remains true from development through adulthood and into older age. What changes is the style of adaptation, the speed, and the degree of flexibility in particular systems. Some parts of the brain are more ready to reorganize than others, and this can vary with age. Sensory systems, motor systems, and areas involved in complex planning do not all mature on the same timeline. They also do not all age in the same way. Plasticity is not uniform. It is distributed, local, and dependent on the specific circuits involved. The overall picture is not of a brain that stops changing, but of a brain that continues to change in quieter, more selective patterns. Learning across the lifespan can be imagined as a steady process of tuning. Early life may involve large adjustments and rapid growth. Later life may involve smaller shifts, careful refinements, and the strengthening of efficient roots through familiar networks. Through it all, repetition plays its calm role, gradually increasing the likelihood that certain pathways activate together. And rest plays its calm role as well, allowing the brain to stabilize changes, to reset chemical balances, and to support the long-term maintenance of circuits. In this way, plasticity is continuous. It persists, not as a constant intensity, but as an ongoing capacity. It adapts to age, to experience, and to the brain's need for both flexibility and stability. The brain changes as we learn, and it keeps changing, with a pace and pattern that shift gently over time, like a slow current that never fully stops, but simply moves in different ways as life unfolds. When people talk about learning, they often imagine a single memory being placed into the brain, as if it were stored in one location. In reality, learning tends to look more like a pattern spreading across a network. Many small changes, in many places, become coordinated over time. The result can feel simple from the inside, like knowing a fact, performing a skill, or falling into a familiar routine. But underneath, the brain is working in a quiet, distributed way, adjusting connections and timing across multiple systems. One useful way to describe learning is to separate it into a few broad categories. There is declarative memory, which includes facts and events that can be brought to mind and described with words. There is procedural learning, which is the gradual shaping of skills, like typing, playing an instrument, or riding a bicycle, where the body seems to know what to do even when words are hard to find. And there are habits, which are patterns of behavior that can become automatic, triggered by context and repeated experience, sometimes with very little deliberate thought. These categories overlap, and they can cooperate. A person might learn the rules of a game in a declarative way, then practice until the moves become procedural, and later find that certain choices become habitual. The brain does not draw strict borders. Instead, it uses different styles of learning that blend together, with slightly different circuits taking the lead at different times. Declarative memory is often associated with the hippocampus, a structure deep in the brain that is involved in forming new memories of events and relationships. The hippocampus can be thought of as a kind of organizer, helping link together the elements of an experience, where something happened, when it happened, what it was connected to. Over time, many declarative memories become more supported by networks in the cortex, the broad outer layer of the brain that participates in perception, language, and conceptual knowledge. In a calm sense, this shift is not a transfer like moving an object from one box to another. It is more like a gradual rebalancing, as cortical networks build their own stable patterns with repeated reactivation. Procedural learning, the learning of skills, is often linked with the cerebellum and parts of the basal ganglia. The cerebellum, located toward the back of the brain, is involved in timing and coordination, smoothing movements and making sequences more precise. The basal ganglia, a set of deep structures, are involved in selecting actions and shaping routines through repetition and feedback. Together with the cortex, these systems can tune a skill so that it requires less conscious effort, and so that movements and choices flow with fewer pauses. Habits are often associated especially with the basal ganglia, and with the way certain cues and contexts can lead into a well-worn sequence. A habit can be seen as a network-level shortcut. Instead of evaluating each step from scratch, The brain recognizes a familiar situation and follows a path that has been strengthened by repetition. This does not mean habits are separate from thinking. It means that with time, some patterns become easier to start and easier to complete, because the connections supporting them have been reinforced again and again. Across all of these forms of learning, the basic ingredients are familiar. Neurons communicate through synapses, and synapses can change. When a pattern of activity happens repeatedly, the synapses involved may become more effective, making the pattern more likely to occur again. This is not a single switch turning on. It is a gradual shift, like a path becoming smoother each time it is walked. Other connections may weaken when they are used less. The brain is always balancing stability and flexibility, keeping what remains useful while staying capable of change. Learning is also rarely confined to one region. Even when the hippocampus is especially active in forming new declarative memories, the cortex is present too, representing meaning, perception, and language. Even when the basal ganglia are shaping habits or procedures, the cortex is still involved in planning, attention, and the representation of goals. The cerebellum can contribute not only to movement but also to the timing of mental sequences. What changes with learning is not only which areas are active, but how well they coordinate, how efficiently signals flow, and how reliably a pattern can be recreated. With repetition, coordination becomes smoother. Early in learning a new skill, many brain systems may be engaged at once. There may be more conscious monitoring, more effortful attention, more checking and correcting. Over time, as synaptic changes accumulate, the burden can shift. The same task may require less monitoring, not because the brain has become less active, but because the activity has become more organized. The networks involved may communicate with fewer unnecessary detours, as if the timing between them has been quietly refined. Rest is part of this refinement. During periods of rest, and especially during sleep, the brain continues to process experience in a slower, quieter way. Patterns of neural activity that occurred during the day can be replayed or reactivated, helping stabilize certain connections. In the hippocampus and cortex, this reactivation can support the gradual strengthening of declarative memories. In circuits involved in skills, rest can support the smoothing and consolidation of sequences, allowing the next performance to feel slightly more settled, even without additional practice in between. It can be calming to remember that learning does not always feel like learning. Sometimes it feels like confusion, followed by a small clearing. Sometimes it feels like familiarity appearing without effort. Sometimes it feels like a habit forming silently in the background. The underlying process is still the same general kind of biology. Neurons adjusting their connections, networks shifting their balance, and multiple systems coordinating their timing. Across the lifespan, these processes continue, though their pace and style can change. In childhood, many forms of plasticity are especially strong, and the brain is rapidly building models of the world. In adulthood, learning remains possible, often supported by repetition and by the stability of existing knowledge. In later life, the brain still adapts, sometimes more slowly, sometimes with a greater reliance on established pathways, and still with the capacity to form new patterns. Throughout all ages, learning is not only about adding information. It is about tuning networks, strengthening some roots, pruning others, and finding steady ways to represent what has been encountered. So when a fact becomes easier to recall, when a skill becomes smoother, or when a routine becomes automatic, it is not a single change. It is many small adjustments distributed across the hippocampus, the cortex, the basal ganglia, the cerebellum, and the connections between them. Repetition shapes the pattern. Rest helps settle it. And the brain, in its quiet way, keeps reorganizing itself, moment by moment, night by night, allowing the experience to leave a gentle trace in the networks that carry it. As you think about the brain changing with learning, it can help to return to the simplest picture. The brain is made of many cells, and among them are neurons, which communicate through connections called synapses. Learning does not usually arrive as a single, dramatic event inside the tissue. More often, it is a quiet accumulation of small adjustments. A connection becomes a little easier to use, or a little less likely to activate. A pathway becomes slightly more familiar, or slightly less traveled. In this way, change can be gradual and still be real. When a pattern of activity repeats, the brain tends to treat it as information worth keeping available. Repetition can mean practicing a skill, but it can also mean the steady rhythm of daily experiences, the regular way the senses bring in sound and light, and the consistent sequence of thoughts that tends to arise in similar situations. Repeated patterns are noticed. They are reflected in the timing of signals, the amount of neurotransmitter released, and the sensitivity of receptors on the receiving side. Over time, these small molecular events can add up to synapses that strengthen, making certain signals more efficient to pass along. At the same time, plasticity includes the opposite movement. Connections can also weaken. If a pathway is rarely used, or if it no longer matches the current environment, the brain may reduce the resources devoted to it. Synapses can become less responsive. The probability that one neuron will influence another can drop. This is not a failure. It is part of balance. Strengthening and weakening are both ways of adapting, and both are present in a healthy, flexible nervous system. Plasticity is not only about gaining, it is also about letting go. This bidirectional quality helps the brain avoid becoming rigid. If every experience only strengthened connections, the system would quickly become saturated, with too many pathways competing for attention. By allowing some synapses to quiet down while others become more responsive, the brain maintains a kind of selective stability. It keeps what is useful, and it reduces what is less relevant. The result is not a perfect, unchanging map, but a living network that can stay organized while still remaining open to change. Stability itself is part of plasticity. After repeated activity, the brain tends to stabilize certain patterns so they can be accessed more easily in the future. Stabilization can involve structural support inside the neuron, changes in the shape of dendritic spines, and the coordinated behavior of groups of synapses across a circuit. Some changes happen quickly, within minutes or hours, and others settle in slowly, over days and weeks. This range of timescales allows learning to be both responsive and durable, adjusting to immediate experience while also forming longer-lasting tendencies. Across the lifespan, the same basic processes continue. In early development, the brain is especially ready to form and refine connections, shaped by sensory input and social interaction and movement through the world. Later in life, plasticity is often more selective, and sometimes slower, yet still present. The adult brain continues to remodel itself, not by rebuilding from scratch, but by tuning. Neurons adjust their responsiveness. Synapses shift in strength. Networks rebalance to match new circumstances. Even familiar skills are supported by ongoing maintenance, because using a pathway keeps it active, and not using it allows it to fade. Another calm way to think about this is that the brain is always negotiating between change and conservation. It must remain stable enough to preserve memory, identity, language, and basic skills. And it must remain flexible enough to incorporate new information and new contexts. Plasticity is the name for that negotiation. It is not a single mechanism, but a family of processes that collectively keep the system workable. Small changes, repeated patterns, stabilization, and balance all belong to the same quiet story. Within that story, rest is not empty time. Periods of lower input and lower demand give the brain space for maintenance. When the pace slows, the nervous system can shift from rapid response to quieter processing. Cells regulate their internal chemistry. Networks adjust their overall excitability. Synapses that were recently active may be reinforced, while others may be scaled down to keep the system in range. In this way, the brain is not only shaped by activity, but also by the intervals between activities. Sleep fits into this rhythm as a natural extension of rest. During sleep, the brain cycles through different patterns of activity, and these patterns are associated with consolidation and reorganization. Some synapses may be strengthened, especially those that supported meaningful or repeated experiences. Other synapses may be weakened slightly, a kind of gentle normalization that prevents runaway excitation and preserves sensitivity for the next day. This is not an abrupt reset, but a subtle recalibration. The brain continues working, but in a quieter mode, using different rhythms. Even the idea of forgetting can be placed here, as another form of adjustment. Not all information remains equally accessible, and not all traces are maintained at full strength. Forgetting can reflect the brain's tendency to prioritize what is repeated, what is connected to existing knowledge, and what fits into the broader patterns of life. Weakening a pathway can reduce noise in the system, making it easier for more relevant pathways to stand out. Again, this is not simply loss, it is refinement. If you return once more to the level of neurons and synapses, the process can seem almost simple. Signals travel. Connections respond. Chemical messengers are released and received. The structure of a synapse shifts by a small amount. A dendritic spine enlarges, or shrinks. Proteins are added, removed, and rearranged. The changes are physical, and they are also statistical, altering the likelihood that one event in the network will follow another. Learning, in this view, is a change in probabilities spread across many tiny sites. And because the brain is always active at some level, plasticity is always possible. It continues in calm, ordinary ways, shaped by repeated patterns and by pauses, by engagement and by quiet. It is continuous, and it is reversible in parts, strengthening here while weakening there, keeping the whole system balanced. The brain does not finish changing. It keeps adjusting, softly, in the background, as life continues to bring similar experiences and slightly different ones. So the ideas can circle gently. Neurons communicating through synapses, repetition shaping pathways, stabilization making patterns easier to return to, and balance keeping the network responsive. Change does not need to be dramatic to matter. It can be small and steady. It can move in two directions. It can include building up and letting go. And between periods of activity, the brain continues its quiet renewal through rest, through sleep, and through the ongoing, understated work of keeping its connections in workable order, returning again and again to the same simple process of signals, synapses, and subtle change.